On to the next chapter on moist processes and large-scale tropical dynamics. We have been looking at wave kinematics, prototype systems, wave mean flow interactions, vertical trapping, horizontal trapping, impacts of various basic states on the waves, and so on. And we derived the theoretical waves, their wave number frequency spectra. Then we looked at their typical character speeds, group velocities, etc. But we haven't talked much about moisture dynamics at all. So obviously we cannot do tropical dynamics of the atmosphere and oceans without getting into moist processes. Remember Charney's conundrum, assuming by scaling 10 to the 6 horizontal scale and then wondering where the baroclinic processes would come from, because at that scale the tropical atmosphere is mostly barotropic. Then he argued that convection wipes out the static stability, and you can get baroclinic processes, divergence, vertical motion, and upper level, lower level coupling. So we will add some of those processes here and answer basically a few questions. How are the convective elements integrated to become a synoptic scale area of organized convection? We have already seen some convective regions in terms of OLR, Walker cell, Hadley cell, and so on, but we haven't explained any of the dynamics yet. But we will here try to combine the wave dynamics with what the convection actually does in the context of the waves and the dynamics. Do these collective convective elements feed back onto the basic dynamics of the tropics? So what is the relation between the circulation and the convection and the waves that we have been looking at, especially looking at something like the Madden-Julian oscillation, which is well known for its wave characteristics, but the wave speeds are not what we derived from the theoretical approaches. So what is the dynamics of slowing down the waves? And finally, how are boundary layer parcels raised to saturation? So we looked at forced waves where we put some heating in the middle of the atmosphere and generated waves, and we didn't say exactly how that top heavy heating is generated. So we will look at convection and try to explain those things. The other way to look at it is that we talked about the mean structure of the ITCZ, which is directly related to the convection problem we are trying to look at. So this is the so-called equatorial trough, which is very well defined in the Pacific and Atlantic Oceans. In the Indian Ocean, you can see that it's to the south in the winter time, boreal winter time, when the sun is to the south, but when sun moves north, because of the monsoon and the land being so close to the equator, the ITCZ splits. So you have a marine ITCZ here. By May, June, July, you end up having very complicated structure of the troughs here. We will not address this problem here, but we'll come back to the monsoon later. But we will think about this trough and see how that is related to the heating and the waves and the circulation. So essentially we have already said how the ITCZ is related to the Hadley cell. You have convergence and rising motion in the ITCZ, which hits the ceiling and then goes off towards the poles and sinks, and then there is convergence at the surface, right? So we have to explain all those sorts of things, and we will not talk about the seasonality so much here. We'll come back to that later on, but there is obviously a close coupling between the ocean and the atmosphere, especially where the sea surface temperatures are very warm and the atmosphere can feel the bottom forcing, but also this zonal contrast, which in the low Coriolis effect produces a pressure gradient and winds directly in response to the sea surface temperature gradient and the hydrostatic pressure gradient. So you can see the sea surface temperatures also move back and forth. So without saying so much about the relation between warm temperatures and convection, we will see about the heat exchange between the ocean and the atmosphere. So we are beginning to add some real dynamics here. And remembering what we have already seen before in terms of the zonally averaged, so we are back to meridional longitudinal averaging or zonal averaging and looking at meridional sections. This is for June, July, August, September DJF, and this is the potential temperature and this is the equivalent potential temperature. So this is the dry dynamics and this is the moist dynamics. And we had already talked about how the temperatures increase as you go to higher latitudes, and this we will see in a minute is quite stable to raising a parcel of air from the surface in the dry case. But you can see that here there are some gradients which allow for instabilities. So then this is where the convection and triggering of convection's impact on the stratification and so on begin to play a role. Okay, so we will look at those things. Examples will include easterly waves, which we saw before in chapter 1. So this is the longitude here, and this is time going down, so July and August. So this is westward propagating waves which happen over the Pacific and Atlantic sectors here. We are looking at 5 north to 10 north visible imagery from a satellite. There are various wavelengths and wave speeds we can calculate from the satellite images, and the rectangle here shows westward trajectory around 0 to 20 north. Various let me make that better. Depiction of easterly waves in the Pacific Ocean in the 5 to 10 north band for the period of July-August 1967 using Tyro's visible satellite imagery. Chang's Hofmüller diagram depicts the westward migration of disturbances, so easterly waves, with wavelength of 2500 to 4000 kilometers propagating at speeds of 8 to 10 meters per second. This is the real speed as opposed to the theoretical speeds we have been calculating, with a period of about 4 days. Section between 0 and 20 north for 3-day period. In the red triangle and yellow line in the panel A, depicting the location of westward trajectory along 6 to 9 north. So this is the other 6 to 9 north section showing here as a latitudinal and longitudinal section. Okay, so we will discuss various properties that get modified by not just the basic state that we have been doing thus far, but by convection, and then look at what are the open questions as far as convection is concerned, and how do the so-called convectively coupled equatorial waves compare with the theoretical waves we have been looking at thus far. What are the processes that can explain the coupling and the relation between the surface heat fluxes, elevated heating, and we will see that not all questions are still answered, but we will learn what is already known.